Okay, in this lecture we're going to cover our section 2.6 material on moments and centers of mass. So let's start by considering the simplest case of determining a center of mass, which would be if we have two masses oriented along a line or a rod. So for this problem, let us consider two masses, M1 and M2, which are attached to a rod on opposite sides of a fulcrum at distances d1 and d2 from that fulcrum. So here, according to the law of the lever, this rod would balance if the product of the mass M1 with its distance from the fulcrum is equal to the product of the second mass M2 times its distance from the fulcrum. So imagine this, really we're talking about like a seesaw problem here. If we have a fulcrum and we have some rod which is oriented along that fulcrum, if we put two masses, let's say M1 at a distance of d1 from that fulcrum, and we have another mass, M2, at a distance of d2 from the fulcrum, this seesaw, or this system, will be balanced if the product M1 d1 is equal to M2 d2. So of course, like if you think about two kids sitting on opposite sides of a seesaw, if M2 is less than M1, so that is, if the mass of the second child is less than that of the first, they would have to be sat at a further distance from the fulcrum in order to balance that seesaw. And this is a property known as the law of the lever. So let us suppose that we are trying to find where a fulcrum should be placed on a rod that has two masses oriented along it in order for that system to be balanced. So let's say that we place our two masses on this rod first, and the question is, where should the fulcrum be placed? So let's consider that question. Suppose the rod lies along the x-axis with a mass M1 at some point x1 and a mass M2 at a point x2, and the center of mass, so the point where the system will be balanced, is given by x bar. So the question is, how do we find that center of mass? So let's illustrate our problem here. We have a rod which is oriented along the x-axis, and we have two masses, M1, which is placed at some point along the x-axis, which we'll call x1, and we have a mass M2, which is placed at a position x2 along the x-axis. And the question is, where should we place a fulcrum? At what position x bar along the x-axis in order for this system to be balanced, if we think about this like the seesaw problem. So we know, using the law of the lever, that this system will be balanced if the product of my first mass, M1, times its distance from the center of mass, which would be given by the difference x bar minus x1. So the length of that interval would be the difference in these x values, x bar minus x1. And that would have to equal the product of my second mass, M2, times its distance from the fulcrum, which would be x2 minus x bar. So I now just need to solve this system for x bar. So here I could start by distributing on both sides. I have M1 x bar minus M1 x1 has to equal M2 x2 minus M2 x bar. or grouping all of the terms involving an x bar on the left-hand side of the equation, I would have m1 x bar plus m2 x bar has to equal m1 x1 plus m2 x2. Or factoring out an x bar, I've got m1 plus m2, and this has to equal m1 x1 plus m2 x2. So it follows that x bar would have to equal m1 x1 plus m2 x2 over m1 plus m2. So that is the center of mass, or the point along the x-axis where this fulcrum should be placed, is at the point given by a ratio where our numerator is the sum of the product of our masses with their positions, and our denominator is the sum of the masses. Now we can generalize this discussion to the case where we're putting more than just two masses along a rod. Let's say that we have maybe 10 different masses, or like 10 kids that will be seated on various sides of a seesaw. Where should we place the fulcrum in order for that system to be balanced? So the argument that we've just made here can be generalized, and we arrive at a result given by the following theorem for the center of mass of objects oriented on a line. So let's suppose that we have a set of n masses, let's say m1, m2, up through mn, and these will be point masses located at the points x1, x2, up through xn, oriented along the x-axis. And let's let little m denote the sum from 1 to n of mi. That is the total mass of the system, or the sum of all of our masses, m1, m2, up through mn. So we would define something called the moment of that system about the origin. So that is this is giving a measure of the tendency of our rod to rotate about the origin, as capital M, which will be the sum of the product of our masses with their positions from 1 to n. So that is, we would take m1 x1 plus m2 x2, and so on up through mn xn. And we can therefore define the center of mass for that system as the point x bar, which would be the ratio of the moment of our system about the origin, capital M, divided by the total mass of our system. So the formula that we were looking at in the case of 2 point masses can be generalized, so that we would have m1 x1 plus m2 x2 up through the product mn xn all over the sum of our masses, or the total mass of the system, m1, m2, up through mn. Okay, so now that we have this method for determining the center of mass for some system of objects oriented along a line or along a rod, let's consider the following example. So we are asked here to find the center of mass of a system of 4 objects whose masses are 10 kilograms, 45 kilograms, 32 kilograms, and 24 kilograms that are located at the points -4 meters, 1 meter, 3 meters, and 8 meters along the x-axis. So let's calculate the components that we need here. First, we would look at the moment of this system about the origin, which we denoted as capital M, which was the sum from 1 to 4 in this case, since we had 4 masses, of the product of our mass with its position. So here our first mass was 10 kilograms. We're multiplying it by its position, which was -1, or -4 meters along the x-axis, plus our second mass, which was 45 kilograms, times its position, which was 1 meter along the x-axis, plus the third mass, which was 32 times its position, which was 3 meters along the x-axis, and then plus our fourth mass, which was 24 times its position, which was 8. So this gives us, capital M is 293 if you sum these values. And the total mass of our system, little m, is the sum of our 4 masses, M1 through M4. So that would be 10 plus 45 plus 32 plus 24, which gives us 111. So the center of mass for this system, x bar, is given by the quotient of the moment about the origin over the total mass. So here we would have a 293 over 111. So this is the point or the distance along the x-axis at which we should put a fulcrum in order to balance that system. All right. So let's look at another similar problem. This next theorem is a formula for determining the center of mass of a set of objects which are not oriented along a single line but are placed in the plane. So here we have the center of mass for a system of objects in 2 dimensions, or in a plane. So the problem is similar. Let's suppose that we have a set of n masses, m1, m2, up through mn, and these are point masses which are placed in the plane at the points x1, y1, x2, y2, up through xn, yn. And we will let m denote the sum of our masses, or the total mass of this system. Now we can define the moments of this system about the x or y axes, respectively, by the following formula. So these moments are going to define the tendency of our system to revolve about the x-axis or about the y-axis. So the moment of this system about the x-axis is denoted as capital M sub x, and it is the sum of the product of our masses with the y-coordinates. So of course the tendency of our object to revolve about the x-axis would depend on how far we're placing our masses from the x-axis, which would be their y-coordinates. And similarly, the moment of the system about the y-axis is denoted as m sub y, and it would be the sum of the product of our masses with their x-coordinates. So again, the tendency of our system to revolve about the y-axis would depend on how far our masses are placed from the y-axis, which would be the x-coordinate for those points where we're placing our masses. Then, once we have these moments defined, we can define the coordinates for the center of mass, x bar, y bar, of this system as follows. So the x-coordinate for the center of mass is given by the ratio of the moment of the system about the y-axis divided by the total mass of the system, and the y-coordinate for our center of mass, y bar, is the ratio of the moment of the system about the x-axis over the total mass of our system. So here I mentioned a note, what exactly are these moments? Well, these moments measure the tendency of our system to rotate about the x or the y axes. So now that we have a way to determine the center of mass for a system of masses placed in the plane, let's look at an example. So here we are asked to find the moments and the center of mass of a system of objects consisting of three masses, M1, M2, and M3, at the points P1, P2, and P3, whose coordinates are given in the plane. Okay, so first we have to calculate our moments. We'll start with the moment of the system about the x-axis, which was defined as the sum of the product of our masses with their y coordinates. And here we've got three masses, so we're summing from 1 to 3. So our first mass was 2 times the y coordinate for our first point was 1. Then our second mass was 3, and the y coordinate for that second mass was -2. Then our third mass was 1, and the y coordinate for that third mass was 4. So here we would have 2 minus 6 plus 4 leaves us with 0. And the moment of this system about the y-axis is the sum of the products of our three masses with their x coordinates. So our first mass, again, was 2, multiplying by the x coordinate for that first mass, which was 5, plus 3 times the x coordinate for the second mass, which was 3, and then plus 1 times the x coordinate for that third mass was -2. So we have 10 plus 9, or 19, and then -2 is 17. And the last thing that we need to find our center of mass would be the total mass of our system, little m, which is just the sum of our three masses. So here we would have 2 plus 3 plus 1 is 6. So once we have these components, we can calculate the coordinates for the center of mass as x bar is equal to my, which was 17, over the total mass, which was 6, and y bar is equal to mx, which was 0, divided by the total mass of our system, which was 6, so just 0 there. So expressing our center of mass as a point, x bar, y bar, we would have the point 17, 6, 0 as the center of mass for this system. Now we can kind of visualize this problem in the plane here. So let's suppose that we have in our xy plane these point masses placed at the indicated points. And let's see if it sort of makes sense where we're placing this center of mass. So here our first mass was placed at the point 5, 1. So here would be our first mass, M1. The second mass was placed at 3, -2. And our third mass was placed at the point -2, 4. And these masses these objects that we're placing have, of course, different masses. M2 was the largest of the three. And we said that our center of mass should be placed at 17, 6, 0. So it's oriented along the x-axis at this point 17, 6, so just shy of 3. And that would be our x bar, y bar, denoting the center of mass. We can see it's scaled a little more towards the second mass, M2. So even though the mass M3 lies a fair distance from this center of mass, well, M3 was the smallest of our masses, so it seems reasonable that this center of mass would be a little more scaled towards the points M1 and M2. Now in the last part of this section, we're going to be looking at the center of mass of a plate. So rather than considering individual masses placed in the plane and finding the center of mass, we'll consider maybe taking some plate which occupies part of the plane and determining what its geometric center or center of mass would be. So let's consider the following problem. Suppose that we have a flat plate, which is sometimes referred to as a lamina, which has uniform density, rho, and this lamina occupies a region, capital R, of the plane with area A. So we have some plate in 2 dimensions with very, very thin width. This plate is called a lamina, and it's got uniform density throughout. So it's just as dense at any point as any other. So if we're interested in determining the geometric center of this object, that would be called its centroid. So if we think about a flat plate, if we were to try to balance our plate on the tip of a pen, the question is at what point should we put the tip of our pen so that we could balance that plate perfectly at that point. And this point is called the centroid of that lamina, or sometimes the center of mass of a lamina. So we have a theorem for determining where the center of mass of a lamina should be placed. So let's take a look at what this theorem says. If R denotes the region below the graph of a continuous function, f of x, which is non-negative on some interval from a to b, and rho denotes the density of the associated lamina, that is the plate which occupies that region under the graph of our function from a to b, then the mass of that lamina is given by the integral of the function f of x dx over the interval from a to b times the density rho. So recall here that this definite integral from a to b of f of x dx is giving us the area of our region under the graph of the function from a to b. So that's giving us the area of our plate or our lamina. And then we're multiplying by the density, that is its mass per unit area, in order to find the mass of that lamina. So here we might have, just to illustrate this, in the xy plane, some weird shaped plate that occupies a region under the graph of a function f of x from a to b. So let's say we have a weird shaped plate like this with uniform density rho. The total mass of that plate is given by this integral. Now, as we did for the system of point masses in the plane, we can define moments m sub x or m sub y of this lamina about the x or y axes, which give measurements of the tendency of this plate to revolve about the x or the y axis. And these are defined as follows. So the moment about the x-axis is the integral of 1/2 of my function squared with respect to x from a to b times the density rho. In the moment of my lamina about the y-axis is the integral from a to b of x times f of x times the density rho. Now, once we have these moments defined, we can define the coordinates for the center of mass of our system, x bar, y bar, as follows. So x bar will be given by the ratio of the moment about the y-axis over the total mass of the lamina, which is equal to the integral of x times f of x from a to b divided by the area of our shaded region. And the y-coordinate for the center of mass is given by the ratio of the moment about the x-axis over the mass of the lamina, which is equal to the definite integral from a to b of 1/2 of the function f of x squared times 1 over the area of that region. So really, to find the coordinates for the center of mass of some lamina, we need to calculate A, the area that lamina, or the area of the region that lamina occupies. And once we have that area, we can set up these integrals of 1 over area times either x f of x or 1/2 of f of x squared to find the coordinates for the center of mass or the centroid of one of these plates. So let's consider an example of this. Here we're told to let R be the region bounded above by the graph of the square root function and below by the x-axis over the interval from 0 to 4. And we want to find the centroid of that region. So here, just a little visual of what we're working with. We have some plate or some lamina that occupies the region of the plane bounded above by the graph of the square root function and below by the x-axis over the x interval from 0 up to 4. So we're looking at a little plate that has the shape of this shaded region, and we want the center of mass of that plate. So the first thing that we need to find to apply our new theorem is the area of this region. Now we already know how to find the area under the graph of a function over some interval. It's given by the definite integral of that function, in this case root x, over the indicated interval, in this case from 0 to 4. So here we would have the antiderivative of root x is 2/3 x to the 3/2, and we're evaluating from 0 to 4. So this would be a 2/3 times 4 to the 3/2 would be the same as 2 cubed, which is 8. Minus when we plug in 0, we have 0. So we're left within 16/3 for the area of that shaded region. Now once we have that area, we can calculate the x and y coordinates for the center of mass, which are called x bar and y bar, where x bar is given by 1 over the area. So 1 over 16/3 would be the reciprocal, 3/16, times the integral from a to b, in this case 0 to 4, of x times the function f of x. So here we would have x times the square root of x dx. So let's evaluate this. We have our 3/16 times the integral from 0 to 4 of x times x to the 1/2 would be x to the 3/2 dx. So for an antiderivative, we have 3/16 times 2/5 x to the 5/2, and we're evaluating from 0 to 4. So let's see what we're left with. Here, let's see what our constant reduces to. We have, let's maybe do it like this first. We have 3/16 times 2/5 times 4 to the 5/2. So that would be the same as the square root of 4, or 2, and then raised to the 5th power, which would be 32, or then multiplying by the 2/5, we would have 64/5. And this leaves us with, let's see, our 64 over 16 would give us 4, times the 3/5 would be 12 over 5, or 12/5. And the y coordinate for the center of mass, y bar, is given by 1 over the area, so 3/16, times the integral from 0 to 4 of 1/2 of the function, which was root x, squared dx. So here, factoring out the constant of 1/2, we have 3 over 32 times the integral from 0 to 4 of root x squared, which would just give us x dx. So we then have 3 over 32 times the antiderivative of x is 1/2 x squared, which we're evaluating from 0 to 4. So let's see what we're left with. We've got our 3 over 32, and then we would have 1/2 of 4 squared, or half of 16, which would be 8, minus when we plug in 0, we're left with 0. So let's see what we're left with. This reduces to 3, and then the 8 over 32 would give us a 1/4, so 3/4. So for our center of mass, we would have the point x bar, y bar, which was given by 12/5 and 3/4. So this would be the center of mass of that region. Now, of course, we can verify whether this seems to be correct by plotting this point in our region that we had sketched earlier. So here, 12 over 5 is 2.4. So here we would have an x coordinate, about 2.4. And then 3/4, which would be somewhere around here. So this point shown in red, well, of course, it lies within the region, which makes sense to be the center of mass for that region. And it's scaled a little more towards the right side, or the bottom right side of our figure, which makes sense since that's where the majority of our plate lies. So it seems like this would be correct here. So in the last part of this section, well, let's try to generalize the question that we just posed. Suppose that we're interested in not only the center of mass, or the center of mass not only of a region under the graph of a function, but we might have a region, say, bounded by 2 curves, and we want to find the center of mass of that sort of region. So let's ask the question, if the region R is bounded by 2 curves, let's say f of x and g of x, where f of x is greater than or equal to g of x on some interval from a to b, the center of mass for that region R would be the point x bar, y bar, where x bar is given by 1 over the area of that region times the integral from a to b of x times the difference of our functions, f of x minus g of x, that is top curve minus bottom curve. And y bar is given by 1 over the area of the region times the integral from a to b of half of f of x squared minus g of x squared. So this formula is fairly similar in the case that we have a region bounded by 2 curves. So geometrically, in the xy plane, we're considering some plate which occupies an area bounded between the graphs of 2 functions, f and g of x, over an interval from a to b. So let's say we had a plate shaped like this. What is the center of mass of that plate? Well, it's given by, the coordinates of the center of mass are given by these formulas. So let's look at one last example of this sort of problem. We're asked to find the centroid, or the center of mass, of the region bounded by the line y equals x and the parabola y equals x squared. So let's start by sketching our region. And to sketch a region, we might start by finding the points of intersection of these curves. So if we let the equations for these two curves equal one another, that is x equals x squared, we would find that x minus x squared is 0. Or factoring out an x, we would have x times 1 minus x is 0. And so it follows that x is either 0 or 1. So let's start by finding the points of intersection of these two curves, and then we'll sketch in the curves themselves. So these intersected when x is 0. Now one of our curves was y equals x, so y would also be 0. And when x is 1, in which case y would also be 1. And one of our curves was the line y equals x, so that is the line passing through these 2 points. And the other was the parabola y equals x squared, which is the parabola whose vertex is at the origin, opening upward. So we're looking at the lamina which occupies this shaded region between those curves. Here our top curve was y equals x, bottom curve was y equals x squared. So again, the first thing that we need to find for to make use of our formulas is the area of this region between those curves. So thinking back to our earlier chapter 2 material, to find the area between curves, we would integrate, in this case from 0 to 1 along the x-axis, the top curve minus the bottom curve. So we're finding the area under the upper curve, subtracting the area under the lower. And in this case, we would have an antiderivative of 1/2 x squared minus 1/3 x cubed from 0 to 1, which would give us 1/2 minus 1/3 minus 0, which leaves us with 1/6 for the area of that shaded region. Now, once we have the area, we're ready to find the x and y coordinates for the center of mass. X bar is given by 1 over the area, so 1 over 1/6 would be 6 times the integral from 0 to 1 of x times the top curve minus the bottom curve, which was our x minus x squared dx. So let's see what we have here. We add a constant of 6 out in front. So let's see, actually, if I distribute this, so I'm going to take my 6 times x and distribute it through to what we have in parentheses here. And I would have the integral from 0 to 1 of 6x squared minus 6x cubed dx. So for an antiderivative, I would have 2x cubed minus 6 over 4, or 3/2 x to the 4th, and we're evaluating from 0 to 1. So we would have here a value of 2 minus 3/2. And we subtract what we get when we evaluate at 0, which would be 0. So 2 minus 3/2 leaves us with 1/2. And to get y bar, the y coordinate for our center of mass, we take 1 over the area. So that would give us a 6 times the integral from 0 to 1 of 1/2 of the upper function, which was x squared, minus the equation for the lower curve, which was x squared squared dx. So pulling out the constant factor of 1/2 and grouping it with the 6 that we had out in front already, we've got a 3 times the integral from 0 to 1 of x squared minus x squared squared, which would be x to the 4th dx. So evaluating this, we would have our constant 3 times the antiderivative would be a 1/3 x cubed minus 1/5 x to the 5th, which we're then evaluating from 0 to 1. So that would leave me with a 3 times 1/3 minus 1/5 minus, when we plug in 0, we have 0. So this would be 3 times, let's see, 5 minus 3 would be 2 over 15. So we would have 3 times 2/15. So that would give us 2/5. So then our center of mass would be the point x bar, y bar, which is equal to 1/2 and 2/5. So again, let's maybe sketch that in our figure here to see if that makes reasonable sense. So the x coordinate for our center of mass was 1/2, and our y coordinate was 2/5 or 0.4. So if this is 1/2, we're just below that. So this would be our center of mass. It seems reasonable based off our rough sketch here. So in this section, we've determined how to find the center of mass for objects placed along a line, objects placed at distinct points in the plane, or how to determine the center of mass, or sometimes called the centroid of a lamina that occupies some plane region, say under the graph of a function, or bounded between two functions.